Consider this. Our planet has a sort of blanket made of gases that keeps it warm. This is a good thing. It's called the greenhouse effect. But when we burn fossil fuels like coal, oil, and natural gas to power our homes, cars, and factories, we release a lot of extra carbon dioxide, or CO2, into the air. This extra CO2 makes the blanket thicker, trapping too much heat and changing our climate. This is causing big problems, like more extreme weather and rising sea levels. We need to find ways to reduce the amount of CO2 we're adding to the atmosphere. It's a huge challenge, but science and engineering have some very cool ideas to help us solve it. This is where a technology called carbon capture and storage, or CCS, comes in. Think of it as a 3-step plan to catch CO2 and put it somewhere safe where it can't warm up our planet. The idea is to grab the CO2 right where it's being made, like at a big power plant or a cement factory, before it ever gets a chance to escape into the atmosphere. It's like putting a lid on a smokestack, but a very, very smart lid. This technology doesn't replace the need for renewable energy like solar and wind power, but it can be a really important tool to help us clean up industries that are hard to change quickly. The 3 main stages of this process are capture, transport, and storage. First, you have to capture the CO2. This is the trickiest part, where we separate the CO2 from other gases. Next, you have to transport the captured CO2. This involves moving it, sometimes over long distances, to a place where it can be permanently stored. Finally, you have to store it. This means injecting the CO2 deep underground into carefully selected geological formations, where it will be locked away for thousands of years, or even longer. Each step has to be done carefully and safely to make sure it works. By following these 3 steps, we can significantly cut down on the amount of CO2 that our essential industries release. Imagine a world where our power plants and factories could operate without adding to climate change. That's the goal of CCS. It's a way for us to take responsibility for our carbon emissions and actively work to protect our one and only home, planet Earth. It's a big job, but with science as our guide, we can figure out how to do it. It's all about finding clever solutions to our biggest problems. Let's get started. The first and most important step is called capture. This is where we grab the carbon dioxide. Most of the time, this happens at big industrial sites like power plants that burn fossil fuels or factories that make things like steel and cement. There are 3 main ways scientists and engineers do this. The first method is called post-combustion capture. In this process, we let the factory burn its fuel as it normally would. Then, as the exhaust gases, the smoke, are about to go up the smokestack, we use special liquid chemicals called solvents to grab onto the CO2 molecules, separating them from everything else. It's like using a chemical sponge to soak up just the CO2. A second way to do this is called pre-combustion capture. This one is a bit different because it happens before the fuel is burned. With this method, we react the fossil fuel with steam and air or oxygen to turn it into a mixture of gases, mainly hydrogen and carbon dioxide. It is much easier to separate the concentrated CO2 from this gas mixture. Once the CO2 is removed, the remaining hydrogen gas can be burned to produce energy. And the best part is that when you burn hydrogen, the only thing that comes out is water. This is a very clean way to generate power, and we've already captured the carbon before it could cause any trouble. The third method is known as oxy-fuel combustion. This sounds complicated, but the idea is pretty simple. Instead of burning a fuel like coal in regular air, which is mostly nitrogen, we burn it in almost pure oxygen. When you do this, the exhaust gas is almost entirely made of water vapor and a very high concentration of CO2. Since there isn't much else in the mix, it's super easy to separate the CO2. We just have to cool down the exhaust to condense the water, and we're left with nearly pure CO2, ready to be transported. Each of these methods has its place, and engineers choose the best one depending on the type of factory or power plant. So, whether we're catching the CO2 after the burn, before the burn, or by changing the way we burn, the goal is the same: to isolate the carbon dioxide. This step is a critical part of the whole CCS process. It's like being a goalie for the planet, stopping the CO2 puck before it can score a goal in our atmosphere. This technology allows us to tackle emissions from sources that are difficult to decarbonize otherwise. It's a powerful tool in our toolbox for building a cleaner future for everyone. Science is pretty cool, isn't it? Once we've successfully captured the carbon dioxide, we can't just leave it sitting at the factory. We need to move it to a permanent storage location, and that brings us to the second stage, transport. To make the CO2 easier to move, we change its state. We put it under high pressure, which turns it from a gas into a liquid-like state called a supercritical fluid. Think of it like this. It's denser than a gas but flows more easily than a liquid. This makes it much more efficient to pump through pipelines or load onto ships, because you can fit a lot more of it into a smaller space. Compressing the CO2 is a key step to making transportation practical and affordable. The most common way to transport large amounts of CO2 over land is through pipelines. These are very similar to the pipelines that have been used for decades to move oil and natural gas all around the world. The pipelines are built from strong steel to handle the high pressure, and they are usually buried underground to keep them safe and out of the way. Safety is the #1 priority. The pipelines are designed with advanced monitoring systems that can detect any leaks or drops in pressure immediately. This allows operators to shut down a section of the pipeline quickly if there is ever a problem, ensuring the CO2 stays contained. For places that pipelines can't reach, like across an ocean or in areas with difficult terrain, we can use other methods. Specially designed ships, much like the ones that carry liquefied natural gas, can transport the liquid CO2 to offshore storage sites. For smaller amounts or shorter distances, tanker trucks or rail cars can also be used. The choice of transportation depends on the amount of CO2 being moved, the distance it needs to travel, and the geography of the route. The key is to have a flexible and secure network to get the CO2 from where it's captured to where it needs to go. No matter which method is used, pipeline, ship, or truck, the entire process is managed with strict safety rules. These rules are in place to protect people and the environment. We have decades of experience moving industrial gases safely, and we apply all of that knowledge to transporting CO2. The transport stage is the critical link that connects the capture of carbon at an industrial source with its final secure resting place, deep beneath the Earth's surface. It's the CO2 delivery service for our planet. The final step in the process is storage, and it's all about putting the carbon dioxide away for good. We can't just release it somewhere else. We need to lock it up so it can't get back into the atmosphere. To do this, we inject the captured and transported CO2 deep underground, usually more than 1 kilometer, or about half a mile beneath the surface. At that depth, the intense pressure keeps the CO2 in that dense, liquid-like state, making it less likely to move around. The CO2 is injected into porous rock layers, which are like giant underground sponges made of stone. These are the same types of rock formations that have held oil and natural gas trapped for millions of years. There are several types of underground locations that are excellent for storing CO2. One of the most common is depleted oil and gas reservoirs. These are old oil or gas fields where we've already pumped out most of the fuel. We know these sites are good at holding gases because they did it for millions of years. Another great option is deep saline aquifers. These are vast layers of porous rock filled with very salty water that is not suitable for drinking or agriculture. They have huge storage potential. A third option is unminable coal seams, which are coal beds that are too deep or too thin to be mined. The CO2 can actually stick to the surface of the coal, keeping it locked in place. Once the CO2 is injected, it gets trapped in several ways. First, it's held in place by a solid, non-porous layer of rock above the storage site, called a cap rock. This cap rock acts like a giant natural seal or lid, preventing the CO2 from escaping upwards. Over time, the CO2 can also dissolve into the salty water in the rock pores, just like sugar dissolves in water. In some cases, over very long periods, it can even react with the surrounding rock and minerals to form new, solid carbonate minerals, essentially turning back into stone. This is the most permanent and secure form of storage. To make sure the CO2 stays put, these storage sites are monitored extremely carefully. Before a site is even selected, geologists study it for years to make sure it's stable and secure. Once injection begins, scientists use sensitive equipment to monitor everything. They use seismic sensors to listen for tiny tremors, sample groundwater from nearby wells to check for any changes, and even use satellites to detect any tiny movements in the ground surface. This constant monitoring ensures the storage is safe and permanent, protecting our environment for generations to come. It's like putting the carbon back where it came from, deep within the earth.
Challenges and limitations. While CCS has great potential, it also comes with several challenges. High cost. Capturing, transporting, and storing CO2 requires expensive equipment and infrastructure. Energy use. The process itself consumes a lot of energy, which may offset some of the climate benefits if that energy comes from fossil fuels. Public concerns. Communities may worry about the safety of underground storage and potential leaks. Limited infrastructure. Many regions lack the pipelines, storage sites, and regulations needed to support CCS projects at scale. However, ongoing research and investment are helping to reduce costs and improve efficiency. Government incentives, carbon pricing mechanisms, and international cooperation are also encouraging broader adoption. Carbon capture and storage is a powerful tool in our fight against climate change. While it is not a standalone solution, it complements other efforts like renewable energy, energy efficiency, and sustainable land use. As we transition to a low-carbon future, CCS can help bridge the gap, especially in hard-to-abate sectors. With continued investment, innovation, and public engagement, CCS can play a key role in creating a cleaner, safer, and more sustainable world.